the paper Jonathan just showed you, which is clean and polished and published and everything. I'm going to show you some really preliminary stuff. And the results I'm going to show you today is actually just based on, so ultimately we're going to be running this in the full UKB. We have some preliminary results in just part of the UKB, and so I'm going to use this to talk a little bit about the design we're doing, but also to comment more generally on G by E effects, because you're all doing these power calculations, right? And so I'm going to show you also maybe what kind of effect sizes you may expect to see in the G by E work that you're going to be doing. And so one of the reasons that I kind of like this approach I'm going to do here is that rather than thinking of the environment as sort of an endogenous thing that may be related to the score, which kind of can lead to complications in interpreting the coefficients, I'm going to have an environmental variable which is plausibly exogenous, and so it is a little easier to interpret as a causal effect. So let's talk a little bit about that. And so specifically, I'm going to be dealing with the question of what's the impact of education on health. And this is a really old question. A lot of people have thought about this. Observationally, there's this weird hand in the way, it seems to hold in just cross-sectional samples. But we want to know what the causal relationship is. And one of the ways that has arisen to commonly look at the causal relationship between education and any other outcome is looking at compulsory schooling law changes. And so when you use, I'll talk a little bit about that more when I introduce the study, but the causal estimates of the impact of education on health are really varied. And so, one study was going to find really large effects and another one's going to find nothing at all. And so there's a great big literature. I have a paper with my colleagues Silvia Barcelos and Leandro Carvalho, who are also my co-authors on this paper, suggesting that there's actually substantial heterogeneity on the effect. And so that means that for one person, if you give them additional education, it may affect their health a lot. And for another person, you give them additional education, and it's not going to affect their health very much. And so our research question of this project is, how does this causal effect of education on health vary by genotype? Can we predict the causal effect of education on health by just looking at a person's genes? Okay, so let's talk about this compulsory schooling law change that we're going to use as our instrument. So in 1972, the UK changed the laws such that, so before you were required to stay in school at least until age 15, and in 1972, you were required to stay in school until at least at age 16. And so people who were born just before and just after this policy change were under different policy environments. Before this change, about 20% of individuals were dropping out of school at age 15. And so this led to a really big change. From 1 year to the next, 20% of people were getting one extra year of education that they wouldn't have gotten otherwise. And so this is a nice clean experiment because we can take individuals who were born just about a week apart even, who should be the same across all observational dimensions, and the only difference is that one group was forced to get more school and one group was forced to get less school. And we can compare the health outcomes of these groups, and if there are differences in the health outcomes for these groups, then those can be attributed then to the additional education that they received. And so to illustrate what this looks like, in the x-axis here is the year of birth, where 0 corresponds to the year that's relevant. So people on this side with negative year of birth values were under the pre-policy environment. They could drop out at age 15. And so the y-axis is the fraction who drop out after age 15, or people who stayed in school until 16 or later. And so you can see in the years before, about 20%, 15 to 20% of individuals were dropping out at age 15. And then all of a sudden afterwards, there's a big jump here in the fraction of students who are getting this additional year of education. So this is a pretty clean, pretty large policy intervention. So what we would like to estimate ultimately is this here. And so y is going to be some health outcome that we're interested in. And this EDGI-16 variable is a binary variable of whether or not an individual was still in school at age 16. We're going to have some controls for date of birth to allow for pre and post trends in the health variables. We're going to have a set of covariates as well. So the way this is going to look different than a standard regression discontinuity design is that rather than just having a single coefficient multiplied by this education variable, I'm going to have some function of our genotype here. And so this means that the effect of education on our health variable can vary depending on what a person's genes are. Now, we can't actually estimate this regression, right, for these endogeneity reasons that I touched on very briefly, but we can use this policy change as an instrument to get at this. And so this is using, I think that some of you had experience with instrumental variables, as we talked about the other day, and so this is the non-genetic Mendelian randomization, if you want to think in that direction. So we're going to use the variation due to the policy change to study the variation in education that's not endogenous. There's no confounds. Yeah?
But this will be identified for the sort of people who switch because of the policy.
Exactly, exactly. And so the numbers that I'm going to show you today shouldn't be thought as just generally the effect of an additional year of education. You should think of it, this is effect of the additional year of education from going to 15 to 16. So it's a more narrow question because of the IV, but it will be well identified. Okay, there's some technical details. We're going to estimate this with a triangle kernel, quadratic trends, and we're going to use people who are just born within 10 years of the policy date. The results I'm going to show are robust. Well, the results I'm going to show are nothing currently because we don't have a large enough sample size, but we're going to do a bunch of robustness checks. The mean effects for analysis that we have done already are robust to different specifications here. But okay, so I've said that the causal effect of education on health is going to depend on a person's genes, and I've not said exactly how I'm going to do that. We could do this a bunch of different ways in principle. What I'm going to do is I'm going to say that the effect of education on health is just a linear function. So there's some kind of average effect here. We're going to have a set of scores, and so this could be a number of different scores, or it could just be one. Ultimately, we're going to include both a score for BMI and a polygenic score for educational attainment. But this could be as many scores as you wanted, I suppose. And then we're also going to have PC controls. And so this is related to what Matt was saying before. If we didn't include the PCs in the interaction here, then the coefficients that we estimate here are going to be confounded by ancestry. And so you need to include the PCs not only as just controls in the whole regression, but they also need to be included in the interaction. And so, just to say, there's a number of things that we could do. So we're going to look at this linear model. We could, instead divide our score into thirds, perhaps, and have a categorical variable or binary variables for low score, medium score, high score. So that would be an alternative specification you could do as well if you wanted something a little bit more non-parametric. So it's, just kind of your choice of what you'd like to do here. Mm-hmm.
What is on the left-hand side of this equation?
So this is this thing here. So this is the causal effect of education on health.
And so are you estimating this? So the equation on the next slide, are you estimating that?
Yeah. So if we were to substitute this directly into here, it would look exactly like these interaction models that we've looked at before, right? Because you would distribute this edu16 variable through this whole thing, and so we would have the direct effect, which is multiplied by the constant, and you'd have the interaction effects that are multiplied here. And so, I write it out this way just to highlight that this is to be a little bit more general and to point out we could write out the interaction however we want. But just to frame this, I'm saying that I'd like to know specifically what is the causal effect of education on health, and I'd like to know what that is as a function of these genetic variables. In terms of estimating, I could have done it. It's pretty straightforward. It's a standard interaction thing, but I think that seeing like this helps interpretation of how I'm going to interpret my results. Yeah.
And then the edu, that it's interacted with, that is just actually whether you're buying like 16 or less, but then instrumented by your birthday relative to the cutoff.
Yes.
And then so then what's the G date of birth?
Yeah. So your health so people who were born longer ago are older, and so their health is going to vary just due to the fact that they're older people.
So that has nothing to do with this sort of natural experiment that you're with the school.
No, yeah, we just need to have that there so that we're not confounded by, it might be that as people approach the threshold, their health is changing, but we want to just see what's happening at that discontinuity. And if we didn't have those controls, then it's going to kind of tilt things and maybe make that bigger. So we're just trying to account for these trends that may exist in kind of the health trajectory. Okay. So we're going to use the UK Biobank. I don't think we've talked in detail about what it is, but the UK Biobank has about 500,000 people. It measures 1 million different things, which is why everyone's so excited about it. It's linked to administrative health data. They had a nurse come in and measure a bunch of objective health measures in addition to responding to these surveys. So as usual, we're going to restrict to just those born in England, Scotland, and Wales, because those are the people affected by this policy change, and we're going to restrict just to those of European ancestry. We don't know, so what would be actually relevant is we want to know which people were living in England, Scotland, and Wales at age 15, and we don't know that, and so we're hoping just those born there is a good enough proxy. We're only going to be identified by people who are living close to this threshold. And as I told you, we're going to use this 10-year window. So once we restrict to those within just 10 years of the window, we're left with about 270,000 people. And then even, for the results I'm going to show you today, the genetic data are only available in about 1/4 of the sample now. And so, you should cut this in 1/4 to think about how many people we're able to use to identify this interaction, this genetic relationship.
So you're essentially looking at the RD amongst a whole bunch of different groups, right? So you've got the interaction between the polygenic scores and the RD. So basically, you're looking at the heterogeneity of the RD effect.
Okay.
In a whole bunch of different groups, right?
Okay. Yeah. I guess sure. Well, I don't know what you mean by groups, but.
Well, different people who are sorted by the different values of the polygenic scores.
Okay, yeah. So because we've done this kind of linear continuous interaction, the way that I would interpret is you could plug in a person's score and their PCs, I guess, and it would tell you what is the expected effect of staying in school till age 16 when you would have dropped out at 15 on this health measure.
So you've shown the discontinuity in the overall population and the running variable, right?
Mm-hmm.
So have you looked at the discontinuity in different groups?
So I'm going to show you that, right? So we're going so in order to estimate, to do an IV, we're going to have to do the first stage version of this thing and then also the reduced form version of this thing. And I'm going to show the first stage, which I think gets at exactly what you're saying. Okay, great. And so, our sample, our sample that we have to identify these genetic effects is maybe about 70,000-ish people right now. So, I've just been abstract. I've been saying why is health? But let's talk about the measures that we're going to use. So I wanted to just restrict to a few measures that I think were likely to be affected by health and that were objective measures. There's lots of subjective measures in the self-reported measures in the UKB, but we had to come up with ways to reduce it, and so we said let's just restrict it to a few things that we think are really solid, direct measures by a health professional. And so we came up with 3 things ultimately. The first is an index based on anthropometric measures. And so this is things like BMI, waist-hip ratio, body fat percentage. And we just combine those into a single measure. We have another measure of lung function, spirometry, which is how people perform in a test where they're blowing into a tube, and it measures how hard they blow and what the volume is that they can blow out. And this is going to be really, really highly correlated with smoking behavior. Also a little bit with activity, but this you could think of this almost entirely as just smoking behavior. And then just a measure of blood pressure. We just take an index of both the diastolic and systolic blood pressure. And then we take the 3 of these indices and we just make one general health index out of the 3 of these. So each pair of these indices has a correlation of about 0.2. So they're getting at kind of different things. And we've also oriented all of these so positive means more healthy. So this is going to be kind of reverse. A high anthropometric score means that you have a low BMI. Okay, great. So let me show you some results. So this is what Remy was asking about. So this is the first stage. And so what I've plotted here is this is the effect of the policy on people who have different scores. And so if you look at this, it's sort of intuitive once you think about it. So on the x-axis is the value of the polygenic score, either the BMI score or the EA score. And here is the change in the fraction leaving school at age 16 or later. And so people who have a low education score were hugely affected by the policy. And this is because a large fraction of people with a low EA score were dropping out at age 15 beforehand, and then all of them were required to stay in school until 16 after. Relative to the people who had a high EA score, very few of them were dropping out. Less than 5% were dropping out at age 15 before. And so it's kind of a smaller, the treatment was smaller in that group. And the BMI score is more shallow, but there still is this interaction relationship here. And so, yeah, so this is kind of interesting, I think. So here's the results of the IV. And as you can see here, there's really nothing much going on. So this is the kind of the direct effect of education. These are the direct effects of the score. And these are the interactions. And there's like, you know, I mean, I guess there's some stars here, but I really don't believe these because these don't hold up very well when we do robustness checks. So I think this is unlikely to hold up once we get all of the data. This one here I think is kind of interesting because even though it's not significant now, it tends to be more robust when we try a million different specifications. And I think it tells a cute story. So if you think about, so look at this coefficient here, it's positive, which means that an additional year of education for just kind of an average person improves their anthropomorphic health. So you can think of it as decreasing their BMI. A person has a more healthy weight if you give them an additional year of education. However, we have a negative coefficient here in the interaction, which means that if a person has a high BMI score, so they're kind of more genetically at risk for obesity, you should add these two coefficients together to get at the causal effect for that person so it's smaller, which means a person who has a high risk for obesity, if you give them additional education, it has a smaller effect on their BMI than a person who has a low genetic risk for obesity. Again, I mean, we're going to have to see if this holds up in the replication, but that's kind of the way that we can interpret these stories, to say, like, this is the effect of the BMI, of education on these different groups.
How should I think about the units?
So these are so each of these outcome measures are in standard deviation units of the index. Yeah, we've standardized all of these.
That's not the real end right now. That's like the.
So well, yeah. So we've ultimately estimated this when a person was missing their genotype data, we coded them as exactly 0, and then we also include an indicator variable to highlight those who didn't have their genetic data. And so what that's going to allow us to do is use the full sample to estimate some of these main effects, but these genetic effects are identified only off of people with genetic data. So you know, and that's true as long as the individuals who have been genotyped are effectively randomly assigned, which is probably true, but it doesn't really matter. When we get the full data, that's not going to, you know, this should all just be okay. In terms of what to expect, so right now, when we get the genetic data, we're going to be increasing our sample size by about a factor of 4. And so if you want to get a sense of how precise these estimates are going to be in the full data set, you can cut these standard errors in half. And so that's why, you know, once this is cut in half, we'll definitely be well powered to see if something this large holds. You know, I think this will probably go away. I think this is over. Oh, why might this be overestimated? Winner's curse. There's a lot of coefficients here. And so the biggest one of all of them, which is this one here, is likely to be too large. And so that's one of the reasons why I think that's going to disappear. Mm-hmm.
Have you looked at the three-way interaction? I know you're probably not powered to do that.
Interacting which?
The BMI score, the EA score.
Oh, interacting these two and?
The edge of 16. You're probably, I'm sure you're not powered right now, but maybe in the low G16.
I mean, I guess, yeah, I mean, you'd have to just think about what that would mean to be. I guess you'd say, what's the effect of having a high BMI and a high EA score? I mean, yeah. I mean, if that's what you're interested in, you could do that. I mean, I think that it's likely to be small, and then as you add more terms, you're less and less powered because you have to, you know, you're doing more and more tests. So, I mean, but one could do that. I have no idea even how to calibrate. Well, so let's talk about the power next. So this is what I want to. So we've had a big lecture about this. If your sample sizes, sample size number. Oh yeah. So the current results I showed you, I have no idea what's going to hold up. And because this is underpowered, if we just said, oh, we're done, and I reported like the spirometry result, it's like, oh, this is what we've learned. I'm not sure that you should really trust it, because when we're low powered like that, false discovery rate's high. Our true effects are going to be inflated away from zero. And so the question is, if we're underpowered, I said this is a claim about what happens when you're underpowered. Well, what does that mean? Well, it's a function of what you think is reasonable. And so this slide contains a bunch of different papers that study G by E interactions, where they interact a score with some environmental variable in a bunch of different settings. A lot of the people who've are on these papers are here or have been here. But so to give you a sense, so this here is the R squared of the direct genetic effect in these different papers. And so this is on the order of between 2 and 7% or so. The environmental effect very much varies, and it depends on what kind of environmental variable you're using. In general, you can see that when the environmental variable is observational, this tends to be larger. And so this is the Belsky paper that you read. And so all of his environmental variables were things just like SES and observational kinds of things. I'm trying to remember which paper this one is. What's the Ocbay paper here that's really large? That's not the Swedish reform, is it? The Swedish reform is this one.
No, that's the EA2 with the...
Oh, this is from EA2, yes. It's the application in EA2. And so again, this is an environmental, like an observational measure, not one that's supposed to be like a causal, a policy change kind of thing. And so these are large. This is the exception. This is the first stage that I showed you before. But you can think of this as, even though this is a policy variable that affected this, it's kind of like a first stage effect, because this is, the effect of the intervention is equal to the fraction of people who were dropping out at age 15 before, and because they were all required to come back in later, the intervention could be pretty large. So this is the exception. But you can see that these two, though, are actual policy interventions due to compulsory schooling law changes, and those are all very small. And this is, I think, a general principle, again, to think about when you guys are doing your own work. If you're doing G by E and your environmental variable is just an observational, not necessarily exogenous thing, then you can maybe expect to have larger numbers here, which are going to correspond to larger numbers in the interaction. If you're doing a G by E where the environmental variable you're looking at is like exogenous, then that tends to explain a lot less of the variance, and therefore the interaction is going to explain a lot less of the variance. You can see this number here corresponds to kind of where we are. Our G by E, given the current estimated effect size, has an R squared of 0.01%. It's very, very, very small, which means we're going to need really large samples. How large? Well, we can pull out our power calculator and work this out. So these columns are if we just wanted to say what's the likelihood that the p-value is less than 0.05. If we want to do a Bonferroni correction, because when you do an interaction, you have three variables. You have both direct effects and the interaction, so it maybe is more appropriate to think of significant as 0.05 divided by 3. And so these are the R squared values in different settings. So the one that we're in this Rosla paper that I'm showing you is this right column. The R squared of the interaction effect is about this big. And you can see that even as you get up to 20,000 people, you only have power of 29% if you're using this threshold, and only 16% if you use the Bonferroni corrected threshold. Once you get up to 100,000, you have power about 90, 80% at that point. And so this highlights just, if you're doing these interactions, how large sample sizes you really need. Depending on the setting again, especially if you want to look at causal effects and exogenous variation in the environment. When the UKB, the full sample of the UKB comes out, this is going to be about like 250,000, just to remind you. So we should be pretty good once we get there. So yeah, conclusion, all the things that I just said. For interactions of the magnitude that we're seeing in our data, you'll need these really large samples to do it. And so keep this in mind as you're thinking about your own G by E work. in our cases, oh yeah, so well-identified cases. So if you're doing these causal exogenous variations in E, those are often an order of magnitude smaller, the G by E things. So that's another thing to keep in mind. And you really need to think about these power calculations again in your own things. Power. Great. That's all I have. Yeah.
I was wondering with the EA score, are you using the EA3 here?
That's actually a good point. So I'm using, this is based on the EA2 score and the BMI Locke et al. Score, which was like 2014 or something like that. And so if we could do things, so like when EA3 comes out, this column would go up to like maybe 11% in whatever sample you have. And so I would think that some of these would be inflated also by that amount. And so.
Yeah, but I was going to say with that, so UK Biobank was a big part of the EA3 sample, right?
Mm-hmm.
So is that going to hurt your power on the...
Yeah, so I've been thinking a lot about this issue. So the idea is, the reason that we're able to get this really large R squared with the EA3 score is because the UK Biobank is going to, add a lot of power because it's so enormous. And so we don't want to use the score that was estimated in the UK Biobank to do any of this work. And so all of a sudden, maybe we're going to be back down to just 5-6%. There's two things that I want to try to do to deal with this. So one of which is that we've thrown out half the sample because they're not close enough to the threshold. And so we could use half of the UK Biobank to boost the power of the score because they're not in our sample for this particular research design. So that gets us 250,000 people or so, or maybe 200,000. Another thing that I kind of like the idea of that I want to do is hold out like 10% of the UKB and do a GWAS on the 80%. And then you can create a score for that 10% based on this 80%, right? Or did I say 10 and 80? Yeah. So like 10% and 90%, even better, right? And so now this score is fair. You can use it to predict for these individuals. But then you can hold out a different 10% and do a GWAS in the 90% and create a score for that. And so it's essentially, it's like a cross-validation procedure. And you could create scores for everyone in the biobank that uses most of the biobank data. I think that creates some funny problems for your standard errors. I have a friend who's kind of working on these issues. But you would in principle get a more predictive score that allows you to use more of your data. But it's computationally, maybe it'll work. I mean, ideally, right, we would just leave out the one person and create a score based on everyone else. And you could do that 500,000 times. But that would take months. And so you have to kind of choose how large a cross-validation you'd want to do. Yeah.
Have you thought about dealing with sample overlap with the, using some of the UKB sample to estimate the score and then testing on another part of the UKB that is related individuals in the sample?
Okay, yeah, so that could be a problem. So like, let's say that you had cousins in your sample. And so if I did this cross-validation thing, and I left out a person, and so I'm like, okay, but their cousin is in the prediction sample, then I've not exactly left out this person, right? Because a bunch of their genes and their common environmental factors are going to be living over here. So I mean, I guess you could deal with that using like, I mean, there's ways we can identify cousins using genetic relatedness and things like that. So you could make sure that those related people are always in the holdout group together. I mean, this is just an idea. I've not implemented it, but that's a good thing, a consideration you need to worry about.
We could just like forget about genetics for a second, and like, how do you feel like this paper fits into that like education and health literature that you sort of talked about?
Yeah. So I told you that there's a big, a big variety of papers that all say different things about this relationship. So one of the papers that I cited earlier about the heterogeneous. I mean, our claim in that paper is that the reason, a part of the reason why everyone's estimating different things in terms of the effect of education on health is that the effect of education on health is different. And so if you have a sample where, people are not largely affected, then it can be, and then a different sample where you have a bunch of individuals that are, then you might see some differences there. So for example, one of the big differences that we see in heterogeneity is if you just take individuals who have a healthy BMI, and you look at the impact of education on BMI in that group, there's nothing that happens. Education doesn't affect the BMI of people who already are healthy. Whereas if you look at the effect of education on BMI for people who have a high BMI, you see actually pretty substantial decreases in BMI for that group. And so, it's a little bit like what you might expect. Well, I mean, it's kind of what I expected, but you could come up with models, I suppose, that are different. But and so this is just getting at this idea of, this heterogeneity thing again. It's like, well, we see that people are, the effect of education on different people is different, and can we identify these people? Can we pick out the people who are most likely to be most affected? Great. I think we're probably good, huh? Great.